Today we're going to be talking about Chapter 5, Section 3, Electron Configuration and the Periodic Properties, specifically about the atomic radius. The boundaries of an atom are fuzzy, and an atom's radius can vary under different conditions. To compare different atomic radii, they must be measured under specific conditions. Atomic radius may be defined as 1/2 of the distance between the nuclei of identical atoms that are bonded together. For example, here we have two chlorines that are bonded together, and you see the difference between the nuclei of one chlorine atom to the other is 200 picometers. So then if you divide that by 2, you see that the atomic radius of each chlorine atom is 100 picometers. Atoms tend to be smaller the further to the right they are found across the periodic table. The trend to smaller atoms across the period is caused by increasing positive charge on the nucleus, which attracts electrons towards the nucleus. So the more positive they are, the electrons are attracted towards the positive nucleus, pulling them tighter together. Atoms tend to be larger the further down the group that they are found, and that trend is due to the increasing size of the electron cloud around an atom as the number of electron sublevels increases. So the more sublevels you get, the larger the area is around the nucleus. Here's a chart on the periodic table that shows you that the size of the radius increases as you go down the periodic table, and it increases as you go to the right. Notice they've labeled cations on the left-hand side of the periodic table. They are ions with a positive charge. So as you're memorizing your ions, notice that the cations, the ones with positive charges, will be on the left-hand side of the periodic table. And they will bond with the anions on the right-hand side, which are the negatively charged ions. And an ionic bond then will form between the cations and the anions. Let's try a sample problem. Of the elements magnesium, chlorine, sodium, and phosphorus, which has the largest atomic radius? All right, so now you want to look at your periodic table and compare the different, compare these. And you will notice that all of these are on the third period. And so then, knowing that they increase, they're larger on the left-hand side, you would look to see that sodium is in the first position 1, or group 1. So sodium has the largest atomic radius. Of the 4, it's the first element in the periodic table. So remember, the atomic radii decreases as you go across the period. All right, now let's move into ionization energy. An ion is an atom or a group bonded of atoms that has a positive or a negative charge. I kind of mentioned that earlier. Sodium, for example, easily loses an electron to form a positive cation. Any process that results in the formation of an ion is referred to as ionization. The energy required then to remove one electron from a neutral atom of an element is the ionization energy. We could call that IE or IE1, which would be the first ionization energy. All right, let's watch our visual.
An ion is an atom, radical, or molecule that has gained or lost one or more electrons and has a negative or positive charge. For example, when a sodium atom loses an electron, it becomes a sodium ion. Sodium ions have a positive charge. Other atoms become ions by gaining an electron. For example, when a chlorine atom gains an electron, it becomes a chloride ion. Chloride ions have a negative charge.
I also want you to take a notice of where they're located on the periodic table. Sodium is in group 1, so we give that a +1 charge because it has one electron in the valence electrons. And in group 17, or the second to the last group, is where chlorine is. And it has 7 valence electrons, meaning it only needs one more to have a full electron orbital, or acting as a full electron orbital. So they are both very reactive, and very reactive towards each other, where the chlorine will take the available sodium ion in an ionic bond. In general, ionization energies of the main group of elements increases across the period. This increase is caused by increasing the nuclear charge. The higher the charge, the more strongly attracts the electrons in the same energy level. Among the main group of elements, ionization energies generally will decrease as you go down the groups. The electrons removed from atoms of each succeeding element in a group are in higher energy levels, further from the nucleus. The electrons are more easily removed. Let's watch another visual.
An ion is an electrically charged atom. If the ion has more protons than electrons, it is a positive ion or cation. If it has more electrons than protons, it will be a negative ion or anion. Ionization is any process that causes a gaseous atom to become electrically charged. A sodium atom is ionized when energy is added to remove an electron. The amount of energy required to do this is called the ionization energy. Ionization energies differ among atoms. This table shows the ionization energy required to remove the first electron from an atom. Once an electron is removed from a neutral gaseous atom, the atom becomes positive, and its remaining electrons are held more tightly to the positive nucleus. Additional ionizations to remove a second or third electron require increasingly more energy. A gaseous atom can also ionize by gaining electrons. Most atoms release energy in this process. This energy represents the atom's electron affinity. Electron affinity can be thought of as the tendency of an atom to accept electrons. Atoms with high electron affinities tend to form negative ions more easily than those with low electron affinities.
Okay. Okay, so here is a chart of the first ionization energy versus the atomic number on the periodic table. So you notice that lithium is in group 2 or group 1 in period 2. And compare that to neon, so which is in period 3. Which is the noble gas within the same period. So left to right, look at how it greatly increases. So as you go left to right, they increase. However, as you go down the chart, notice the difference then now in period 7. It does still increase, but as you go down the chart, the increase is far less substantial. So now let's look at a problem. Consider two main group elements. They're A and B. We don't know what they are. Element A has a first ionization energy of 419 kilojoules per mole. Element B has a first ionization energy of 1,000 kilojoules per mole. Decide if each element is more likely to be in the S block or P block. Which element is more likely to form a positive ion? Now go back to that couple of charts that we were looking at, and increasing ionization energy, lower to higher, and that should be able to help you. All right, element A, notice, has a low ionization energy in comparison to element B, which means that the atoms of A will lose electrons more easily. So element A is more likely to be in the S block metal because the ionization energies increase across the periods. Element B has a higher ionization energy, which means that the atoms of B then will have more difficulty in losing their electrons. So B would most likely be at the end of the period or in the P block. Element A then is more likely to form a positive ion because it has a much lower ionization energy, which also remember the cations are on the left-hand side of the chart, then do the element B's, and remember the anions are on the right-hand side of the chart. Periodic table is what I'm referring to as chart. All right, the electron affinity is when the energy change that occurs when an electron is acquired by a neutral atom. So that's the electron's affinity. Electron affinity then generally increases as you go across the periods. Increasing nuclear charge along the same sublevel attracts electrons more strongly. So the electron affinity then generally decreases down the group. The larger the atom's electron cloud is, the further away it is from its outer electrons are from its nucleus. Let's watch this visual concept.
Some elements acquire electrons to form negative ions. In the case of chlorine, the formation of a negative ion is favored because the resulting chlorine has a full octet. In general, the closer the atom is to acquiring a full octet, the more strongly it attracts electrons. Chlorine has 7 valence electrons, and its electron affinity is negative 361.7. By convention, the more negative the number, the more strongly the atom attracts the negative electrons. Phosphorus has 5 valence electrons and an electron affinity of only negative 74.6. The electron affinity of aluminum with 3 valence electrons is negative 44.1. Because of the way electrons form orbitals, there are some lapses in this pattern. Nevertheless, the general trend holds.
Okay. Ionic radii. A positive ion, we said, was called a cation. The formation of a cation by the loss of one or more electrons always leads to a decrease in the atomic radius. And that makes sense because the electron has been removed, allowing then the radius to be smaller. The electron cloud then, like we said, becomes smaller. The remaining electrons are drawn closer to the nucleus by an unbalanced positive charge because they haven't lost the protons in the center, only an electron in the electron or two in the orbitals. So a negative anion or ion is called an anion. The formation of an anion occurs by the addition of one or more electrons, and that leads to an increase in the atomic radius.
If an atom loses an electron, it then has one more proton than electron, and has a positive charge. If an atom gains an electron, it then has a negative charge.
Well, that was exciting. All right, so cation and anion radii decrease across a period. The electron cloud shrinks due to the increasing nuclear charge acting on the electrons in the same main energy level. The outer electrons in both cations and anions are in higher energy levels as one reads down a group. There is a gradual increase of ionic radii down the group. I'm trying to get this quick time visual here.